welcome. Today I'm going to be explaining how infinities work. Yes, infinities plural. It's not that hard. So, as we know, you should probably know the definition of infinity and infinite. But basically, an infinity is, how do I word this? Well, infinity itself is the state or quality of being infinite, according to the dictionary. But it, infinities are larger than any number, as we know. So, you can't do infinity plus one because infinity is still infinity. It's the state of being endless, boundless, and larger than any number, any number whatsoever. So -5 or infinity, positive infinity is greater than 100 octodecillion or something like that. You can't add any more per se to infinity unless it's another infinity, which is where this gets interesting. So let's say that the red represents a negative number. And the pink represents a positive number, like positive 1. Actually, I'm going to change that. Maybe I should find some different numbers. Okay, so here's how it works. Let's say we have 1. Then we have 2, 3, 4, 5, 6, 7, 8, 9, 10. Basically, all whole numbers. So the numbers you learned back in kindergarten, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to that goes endlessly. That's an infinity. So positive whole numbers are all whole numbers. So all positive integers. That is one infinity. Let's say, I know that it won't be accurate, but for today's purposes, we're just gonna call it, set P. P for positive. But, as we all know, there's also a negative number for every positive number. So there's an infinite amount of negative numbers. N for negative infinity. Now let's say we know that both of these both of these are infinite because and there's endless negative numbers and endless positive numbers. So, here's the fun part. As we know, there is something called a number classification called integers. I'll read you the dictionary definition. An integers refers to a number that is not a fraction. So every single one, so even negative numbers like -1, -2, those are integers because they are not fractions. So let's say there's so let's say we are including all integers. I'll just erase that. We'll call this infinity I. Of course, both all the whole numbers and then all the negative whole numbers, so like all the negative integers and all the positive integers are their own infinities, right? Well, yes, but this infinity of I, which includes all integers, is greater than both of them because it includes all whole numbers. So, like any number that's not a fraction, which should include negatives and positives, is part of this infinity. And as we know, yeah, they're positive and negative. I should explain this really quick. Let's say you're confused. I'm certain you are, so one of you. Where does 0 fit in all of this? Zero should be greater than any negative number, yes, but lesser than any positive number. But here's the thing. These infinities aren't in relation to the value per se. For our purposes, we're referring to these infinities as in how many numbers it includes, how many values it includes, numbers. So 0 is a non-factor. But if you were comparing, and let's say someone had, well, here's how it would work. Let's say someone had infinite debt. Like, debt is a minus number because you owe someone else money and it's taking from your money. So debt would be an example of the n, which is the negative infinity. Well, let's say there's someone who has infinite wealth, money. They would be an example of the p. Now, let's say there's you who has $0 now because both of these people have taken all the debt and money in the world. You already have more value than the n in infinite debt because you don't owe anyone anything, money-wise. And, but the infinite wealth will be greater than you. It's greater than you by a ridiculous margin because, well, any positive number is already greater than 0 by like a factor that I can't even really quantify myself. I'm not a mathematical professional or anything, so that, yeah. But any positive number will be greater than 0. And then you have to consider that P, infinite wealth, represents all of those numbers, or how many positive numbers there can be. Endless. So, yeah. Now let's say let's say you are interested, like, oh, you forgot the fraction, sempiternal? Well, I didn't. See, rational numbers are basically any number that is not an irrational number. If you don't know what an irrational number, I'll just read you the dictionary definition. In int So an irrational number is devoid of a ratio, and then rational, like no ratio. And basically that means no fraction could properly represent it. So, no fraction, no number, anything. Pi is a perfect example of an irrational number. An irrational number is also something that, like, think of square roots and cubes and squares. 4 squared is what? 16. And 4's square root is 2. But 2 itself has no square root. Well, it does have a square root, but it's not a whole number. It's an irrational number because it goes on forever. You can look it up in your calculator. I can show you right now, but that would take a long time because I'd be dividing for quite a while. But any number that does not have a whole number or decimal square root is an example of an irrational number. Irrational numbers would be somewhere along the infinity like this. So there's rational numbers, which include this stuff. So RAT is going to represent rational numbers. So it even includes decimals that are repeating. So like 2/3 and 1/3, where it's like 0.33333, and the 3 goes on forever. See, an irrational number doesn't have that. An irrational number, it's a different number for each, the further you go. So like pi. I'm not really good. I can't remember most of pi. But it's not like 3.1444. Pi is 3.141592 and then so on and so forth. This isn't math class in 6th grade or any grade, or so I'm not going to say all pi. That would be weird. But yeah, pi is forever unique. It's an infinitely unique number. It doesn't repeat. The orange is going to represent the irrational numbers. So as you can see, those are some examples of irrational numbers. If you were to put it into a calculator, oh shoot, I can download a calculator, just give me a second. That wasn't as long as I expected, but suffice to say, yeah, if you were to, go to your calculator, you could type in this to see if I'm right. As you can see, the number is not a whole number. It doesn't stop. The only reason it stopped is because the calculator wanted it. The calculator made it stop. It can't show all of the numbers. But yeah, let's try it with a number that is a whole, that does have a decimal or at least a whole number root. 196, which should be 14. Voila. If you were to try something like, I don't know, let's see, 15,625, you should get 125. Or if you were to make a decimal like 6.25, it should be 2.5. Yeah. So even if it has this decimal, it still stops at 1 point. Or even if you were to try something like 1/3, I'm not sure if this will work because 1/3 is a repeating decimal, so I'm not sure if the same applies, but it should. As you can see, I don't think that works out because it's a fraction and it's already repeating. But that's a different story. You can check that out on your own calculator, or you can do the math for it. I don't recommend you do the math for it because you might be stuck there for a long time. But yeah. However, what if I told you there's an infinity that's even bigger than this one? So perhaps some of you who already know this, and I'm confused as to why you're watching this video, know of what should be one of the, what should encompass all of these real numbers. So real numbers include rational numbers and irrational numbers. So real numbers can be expressed by even an infinitely going on decimal, like pi, or the square root of 5. And it can be also positive whole, any of that. But there are also these things called imaginary real and imaginary roots of polynomials. I'm not a high school teacher, or whenever you learn polynomials these days. But yeah, imaginary numbers are not real numbers, as you know, because it literally has the word imaginary in it. But if you're curious, I will give a quick definition. So it basically represents something that doesn't really have a tangible or a real value per se. So, I have a good one. You can't find a negative number square root. A negative number cannot and does not have a square root. I'll even prove it. Undefined values on a calculator means that either A, your calculator is dumb and probably can't find the value, or B, there is no value because it's an imaginary number. So the reason a negative number doesn't have a square root is because it can't. In order to get a negative number, you have to multiply a negative number by a positive number. So, negative 5 times 5 would get you negative 25. But a square, that's not how squares work. So, like, a square, it's the same number. So, it would have to be negative 5 times negative 5, which is positive 25. The negatives cancel each other out. So, that's an example of an imaginary number. Also, dividing by 0 can get you there. I'll do a quick explanation of 0 and then probably hop off. I'll explain higher dimensions in the second part of this video. It's way shorter and way simpler. See, you can't divide by 0, nor can a calculator. Why? Because this. Let's say we were to divide 85 by 0. What number would you get? Sorry, I have the hiccups. What number would you get? You'd think it's 85, right? Because, it's not getting divided into any groups. But that wouldn't make any sense if you're dividing into nothing. But here's the thing. Reciprocals. That's where it all comes back to bite you. If something is divided by 0, then it has to get multiplied by 0 and get you the same number. So, this. Let's say it were 8. Now, I have to multiply 8 times 0, which is 0. It gets really confusing, and I'm not an expert in that. I mean, I know about it, but I'm not sure how I can explain it in a way. But yeah, I'll make a video about it maybe. But next video, dimensional tiering and how higher dimensions work.